Hello friends, welcome back to my YouTube channel. In this class I am going to discuss 3 more problems of chapter 7 of PKNAG's Engineering Thermodynamics. These problems are based upon the concept of entropy and entropy generation. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. A block of iron weighing 100 kg. 100 kg is the mass of iron block and having a temperature of 100 degrees Celsius. The temperature of iron block is 100 degrees Celsius, is immersed in 50 kg of water at a temperature of 20 degrees Celsius. So the temperature of iron block is higher than the temperature of water, and this block of iron is immersed in water. What will be the change of entropy of the combined system of iron and water? Specific heats of iron and water are 0.45 and 4.18 kilojoule per kg Kelvin respectively. So you see, this is a block of iron which is immersed. This is the block of iron which is immersed in water. And so mass of iron block is suppose Mi, which is given to be 100 kg, and the temperature of iron, let it be Ti, and it is 100 degrees Celsius. Let express it in terms of Kelvin, that is 100 plus 273, that is 373 Kelvin, and mass of water, let mass of water be Mw, and Mw is given to be 50 kg, and temperature of water Tw is 20 degrees Celsius, and that is 293 Kelvin. So if you apply the energy balance principle to this combination of iron block and water, first we will consider that this combined system of iron block and water as an isolated system. Suppose this iron and water is an isolated system, that means this is our universe, and if this composite system is isolated, so if you apply an energy balance principle to this, that will be E in minus, this is the energy balance principle, E in minus E out is equal to delta E. Here if you consider this as an isolated system, there is neither any energy interaction into this isolated system nor any energy leaving this isolated system. So these two terms are zero. So now this energy balance principle reduces to delta E equal to 0, or you can say delta Ek, change in kinetic energy of the system, plus delta Ep plus delta U. This is change in potential energy, this is change in molecular internal energy, 0. But for a stationary system, these terms are 0. So now this equation is nothing but change in internal energy is equal to 0. From this, I can say delta U of iron plus delta U of water, because we are considering the isolated system comprising of two subsystems. This is your iron block and this is water. So summation of change in internal energy of both the subsystems is 0. So delta U iron is equal to minus delta U water. Here iron is at a higher temperature, that is 100 degrees Celsius, and water is at a lower temperature 20 degrees Celsius. So let Tf be the final equilibrium temperature. So for finding out change in entropy we have to first find out the equilibrium temperature. Then only we can calculate the change in entropy both for iron block and for water. So from this equation, delta U of iron is MiCi. Ci is the specific heat of iron. Ci is the specific heat of iron. So MiCi Tf minus Ti. This is the change in internal energy of iron is equal to minus of delta U of water will be Mw Cw Tf minus Tw. The final equilibrium temperature will be same for both iron and water, iron block and water. And equating this becomes Mw Cw Tw minus Tf. So on equating this, mass of iron is 100 kg. 100 into specific heat of iron is given to be, this is 0.45 Ci, specific heat of iron. 0.45 multiplied by Tf minus Ti is 373 is equal to Mw. Mass of water is 50 kg. 50 and specific heat of water is 4.187 multiplied by 293 is the temperature of water in terms of Kelvin minus Tf. On equating this, we can find out the Tf. This is one method, and another method is just by applying that heat will be definitely the temperature of iron block is 100 degrees Celsius and the temperature of water here is 20 degrees Celsius. So heat will be lost by iron block and heat will be gained by water. So the final equilibrium temperature will lie in between these two temperatures, that is, it will be less than 100 degrees Celsius and it will be greater than 20 degrees Celsius. And we have to apply the principle that heat lost by iron block is equal to heat gained by water. So same result will be obtained as it has been obtained right now. So either you can apply the energy balance principle or you can simply apply that heat lost by iron block here will be heat gained by water. On solving this equation, we will find that Tf is equal to 307.17 Kelvin. So just by solving this equation, we will easily obtain the Tf. Tf will obviously be less than 100 degrees Celsius, so less than 373 and more than 293, and it will be 307.17 Kelvin. So now we have to calculate change in entropy of iron. Change in entropy delta S of iron. This is equal to MiCi dt upon T, and integration limit is from Ti to Tf. This is equal to MiCi ln of T, limit is from Ti to Tf. This is equal to 100 into 0.45 ln Tf divided by Ti. So this is equal to 45 multiplied by minus 0.1941. This is equal to minus 8.737 kilojoule per Kelvin. Similarly, delta S of water is equal to integral of TW is the initial temperature of water, suppose, and TF is the same final equilibrium temperature. MW CW dt upon T. So this is equal to MW CW ln of T, limit is from TW to TF. This is equal to MW CW ln TF upon TW. TW is the initial temperature of water, TF is the final equilibrium temperature of water. This is equal to 50 multiplied by 4.18 ln TF is 307.17 divided by 293 is the initial temperature of water. So this is 9.8708 kilojoule per Kelvin. Now in the question it is required to find out that what will be the change of entropy of the combined system of iron and water. So combined system change in entropy of this universe is delta S of iron plus delta S of water. This is your universe for this particular problem. This is your universe, and this is 9.8708 is the delta S of water minus 8.737, and unit is in terms of kilojoule per Kelvin. This is coming out as 1.133 kilojoule per Kelvin, and this is greater than 0. Why the delta S universe is this much only, summation of this? Because since this is isolated, there is no interaction with the atmosphere. So that assumption we have to make right from the beginning, that this is an isolated system, iron and water. There is no energy interaction between this isolated system with the surroundings. So when delta S universe is positive means it is an irreversible process. We know from principle of increase of entropy that if delta S universe is greater than 0 means it is an irreversible process, and if it is equal to 0 means it is a reversible process. And we know that when heat transfer occurs through finite temperature difference, this is a case of an irreversible process, and here also the heat transfer takes place through a finite temperature difference. So that is obvious that this is an irreversible process. So next question is 7.32. 36 gram of water at 30 degrees Celsius are converted into steam. 36 gram of water at 30 degrees Celsius are converted into steam at 250 degrees Celsius at a constant atmospheric pressure. The specific heat of water is assumed constant at 4.2 joule per gram Kelvin, and the latent heat of vaporization at 100 degrees Celsius is 2260 joule per gram. For water vapor, assume PV is equal to MRT. You know, when water is in its vapor state, it will behave like a gas. So it will definitely follow ideal gas equation, PV equal to MRT, where R is 0.4619 kilojoule per kg Kelvin, and Cp divided by R will be A plus B into T plus C T square. This will be a function of absolute temperature, where A is this much 3.634, B is 1.195 multiplied by 10 to the power minus 3 Kelvin to the power minus 1, and C is equal to 0.135 multiplied by 10 to the power minus 6 Kelvin to the power minus 2. Calculate the entropy change of the system. So mass is 36 gram of water, and initial temperature is 30 degrees Celsius, and eventually it is converted into a water vapor, and temperature is 250 degrees Celsius. So final temperature is 250 degrees Celsius, and this heating process takes place at constant pressure. So during the process pressure remains constant, and specific heat of water when it is in liquid state is 4.2 joule per kg Kelvin. And latent heat of vaporization at 1 atmospheric pressure is equal to this. HFG is nothing but the latent heat of vaporization, and this heat is absorbed when liquid is converted into vapor at a constant temperature, at a saturation temperature. So 2260 joule per gram, and all other values are given. R values when the water is converted into water vapor, it behaves like a gas. Then characteristic value of characteristic gas constant is given. So if you describe the whole process, that will be like this. This is suppose TI, initial temperature, in terms of Kelvin, that is 30 degrees Celsius, and then it comes to the liquid saturation temperature. We know that at 1 atmospheric pressure, saturation temperature is 100 degrees Celsius or 373 Kelvin. This is saturated liquid state. Saturated liquid state. And same with temperature remaining constant, when it absorbs certain latent heat of vaporization, it gets converted into saturated vapor state. The pressure remaining constant and also the temperature remaining constant during this phase change. And saturation temperature is 373 Kelvin. Then it is converted into a superheated vapor state, and here this substance is in the gaseous state. So from 373 Kelvin to 500, this is final temperature, 250 degrees Celsius, that is in terms of Kelvin, this is 523 Kelvin. From this to this temperature, this will behave like a gas. So change in entropy of water will be delta S of liquid plus delta S of phase change plus delta S of vapor. So delta S of liquid is M of liquid, that is the 36 gram of water. Specific heat of water in the liquid state, dt upon T. So integral limit is from 303 is the initial limit and 373 is the final limit. 373. So this is equal to ml Cl ln 373 divided by 303. This comes out to be 36 multiplied by 4.2 ln 373 upon 303, and so this comes out as 31.426 joule per Kelvin. So when the phase change of water takes place, when it is converted from saturated liquid to saturated vapor, so what is the phase change in entropy? So during phase change, the temperature remains constant, as it happens in case of an entropy change of a reservoir. Whenever if you add heat or reject heat from a reservoir, its temperature doesn't change. So at that time, you just divide the heat added or heat rejected by the temperature of the reservoir. Similar thing happens here. So delta S during phase change is nothing but the mass is 36, and HFG, latent heat of vaporization, 2260 joule per gram. So this is equal divided by 373, and so answer will come out 218.123 joule per Kelvin. Now in the vapor state, when it is heated from this saturation temperature of 100 degrees Celsius to 250 degrees Celsius and attains a superheated state. During this zone, it is in the gaseous state, so obviously it will follow the ideal gas equation. So delta S of vapor state will be mCp dt. T saturation to final temperature Tf. So this will be m, in place of Cp I will write R multiplied by, because you see in the question it is given that Cp upon R is equal to this much. So in place of Cp I will write R multiplied by this much. So R A plus Bt plus Ct square mCp dt upon T. So this will be, integration limit is from T saturation temperature to Tf. So this is equal to mr, both are being constants, can be taken outside the integral sign. So this is T saturation, this is Tf, A by T plus B plus Ct dt. So this is equal to mr A ln T plus Bt plus Ct square by 2 integral of T dt. This is, limit is from 373 to 523 in terms of Kelvin. So this is equal to mr A ln 523 divided by 373 plus B 523 minus 373 plus Ct square by 2. C by 2 multiplied by 523 square minus 373 square. So this is equal to 36 multiplied by 0.4619 multiplied by 3 putting the value of A, B and C as given in the question. 3.634 ln 523 divided by 373 plus B, value of B is 1.195 multiplied by 10 to the power minus 3. So this is 523 minus 373 plus, in place of C I will write 0.135 into 10 to the power minus 6 by 2 523 square minus 373 square. So this will be 16.6284. So this is 1.2283 plus 0.17925 plus 0.009072. So this is equal to 16.6284 multiplied by 1.4166, 23.5566. So change in entropy of system, change in entropy of system is equal to, there are summation of three terms. One is the change in entropy that takes place when the liquid water is heated from 30 degrees Celsius to saturation temperature, that is 100 degrees Celsius. Then the change in entropy that takes place during the phase change process, that is the latent heat of vaporization HFG by T saturation. Then during the third stage, that is when the saturated water vapor is again heated to 250 degrees Celsius with the pressure remaining constant. So now change in entropy will be summation of these three change in entropies, and this is 31.426 plus 218.123 plus 23.5566 joule per Kelvin. So this is equal to 273 joule per 273.1 joule per Kelvin. So this is the change in entropy of water when it is heated from 30 degrees Celsius to 250 degrees Celsius at 1 atmospheric pressure. That is from a subcooled liquid state to superheated gaseous state. So next question is 7.33. The question is like this: a 50 ohm resistor carrying a constant current of 1 ampere, 50 ohm resistor carrying a constant current of 1 ampere is kept at a constant temperature of 27 degrees Celsius by a stream of cooling water in a time interval of 1 second. What is the change in entropy of the resistor? And in the second part, what is the change in entropy of the universe? So you see, there is a resistor through which current flows. So suppose I is the current that flows through this resistor, and this is resistance is 50 ohm, and temperature of this resistor remains constant at 27 degrees Celsius throughout the process. And this current is 1 ampere. (300 Kelvin). Time for which the current flow is 1 second. You see, whenever a current flows through a resistance, there will be a heating effect. Heat will be produced and the temperature of resistance increases. But what happens here? Temperature remains constant. That means the resistance is in a steady state. Its properties do not change with respect to time. So how does it happen? So whatever heat is liberated, whatever heat is released, or whatever heat is produced by the flow of current for a specific time period, then that heat goes to a stream of cooling water, which takes away the heat liberated by this current. So that's why the temperature of resistance doesn't increase, it remains constant at 27 degrees Celsius. So here some cooling water is there. Heat that is produced here goes to this cooling water. So now we can say that if you want to calculate the change in entropy of resistor, means this resistor is already in steady state because its temperature doesn't change. So whenever a body is in steady state, means its properties don't change with respect to time. So that's why change in entropy of resistor is 0 because it is already in the steady state. Change in entropy of resistor, delta S of resistor is 0. But what about the delta S of universe? So to find out that, here resistor is there and in its vicinity there are some water, cooling water, stream of cooling water which flows nearby. So we have to calculate the change in entropy of that water and add it to the deltas of resistor to find out the deltas of universe in this case, because here the universe consists of these two subsystems. One is wire and other is the stream of cooling water. So you see how the temperature of a resistor remains constant at 27 degrees Celsius, because whatever heat is produced by the flow of current for a specific time period, that heat is liberated and that heat goes to the stream of cooling water. So I can say heat absorbed by water here. We want to calculate the entropy change of water. So how to calculate the entropy change of water? We have to calculate the heat absorbed by water. And you see heat absorbed by water here is same as heat liberated by resistor. Why heat is liberated by resistor? Because this is in the steady state. That means its temperature doesn't increase. So how is it possible? Whatever heat is produced by the flow of the current through it is rejected away or is taken away by the cooling water, stream of cooling water. So heat absorbed by water is I square R multiplied by T. T is the time. One current, the flow of current is 1 ampere. So 1 ampere multiplied by resistance is 50 ohm multiplied by time is 1 second, and so this is 50 joule. So delta S of water will be, you see the temperature of water remains constant at 27 degrees Celsius. So that means change in entropy of water will be whatever heat comes to it, that is 50 joule divided by temperature of water is 27 degrees Celsius, and in terms of Kelvin that will be 300 Kelvin. So this will be 0.1667 joule per Kelvin. So if you want to calculate delta S of universe, that is equal to delta S of resistor plus delta S of water is equal to 0 plus 0.1667 joule per Kelvin. This is equal to 0.1667 joule per Kelvin. Thanks for watching. And this is the entropy change of universe. So it is positive and it indicates that it's an irreversible process. So thanks for watching.